Good evening. Good evening. I would like to welcome you all here. I am Persis Drell. I'm the Dean of Stanford School of Engineering, and I'd like to thank you for joining us tonight. Not only do we have a full house here in NVIDIA Auditorium, but we're webcasting live on YouTube to alumni, students, and friends around the world. What that means is when we get to the Q&A, at the end, we will want to repeat your questions for the online audience. So we are here tonight to honor Perry McCarty. He is the Silas H. Palmer Professor Emeritus in Stanford Engineering's Department of Civil and Environmental Engineering. The HEROES program at Stanford Engineering is now in its 5th year, and we use it to recognize the achievements of Stanford engineers who have been able to really profoundly advance the course of human, social, and economic progress through engineering, and who in addition are just wonderful people. And Perry fits that bill perfectly. Our heroes personify the mission of Stanford Engineering to seek solutions to important global problems and enrich humanity by using engineering principles, techniques, and systems. Their life's work demonstrates a commitment to not just advancing technology, but also changing the world for the better. And they embody leadership qualities that inspire future generations of engineers to apply their education to have a positive global impact. Now, along with Perry, this year's inductees include Netflix co-founder Reed Hastings and Dr. Martin Fisher, the founder of Kickstart International, an award-winning nonprofit social enterprise that develops technologies to improve lives and lift people out of poverty in developing nations. They join a very distinguished group that includes luminaries such as Fred Terman, Sally Ride, former U.S. Secretary of Defense and Stanford faculty member Bill Perry, and Irmgard Flugelotz, who was renowned for her many important contributions to aerodynamics and automatic control theory. But let's talk about Perry. Perry McCarty is best known for his research and teaching on water, with a primary interest in biological processes for the control of environmental contaminants. And I think we're all going to learn a little bit more about that this evening. He's recognized as one of the world's foremost authorities on microbial processes used in the treatment of water, the treatment of wastes, and the treatment of hazardous chemicals in the environment. He's devoted his career to the discovery of how to create micro-environmental ecosystems to cleanse water of human waste and reduce groundwater pollution. And I think you're all aware of just how important this issue is. Perry joined the Stanford University faculty in 1962 when he came to help develop the Environmental Engineering and Science program. He just told me a lovely story of how his family drove across the country and spent their first night in the tent cabins in Tuolumne Meadows. What an introduction to California, I have to say. From 1980 to 1985, he was the chair of Stanford's Department of Civil and Environmental Engineering, and from 1989 to 2002 served as the director of the Western Region Hazardous Substance Research Center. By his retirement in 1999, Perry had trained 40 PhD students, half of whom went on to teach at universities, which is an amazing legacy. And of those, 11 became department chairs and 1 a dean. He's authored some 350 peer-reviewed papers. He's written 2 textbooks, Environmental Biotechnology Principles and Applications, and Chemistry for Environmental Engineering and Science. They were co-authored with former students Bruce Rittman of Arizona State University and Gene Parkin of the University of Iowa, and together have sold more than 200,000 copies. And they are standard texts for a profession that is dedicated to counteracting and mitigating the environmental degradation, pollution, and waste of the industrial age. Now, I looked at that number and I 200,000? I mean, I think that's a bestseller in that field. Very, very impressive. Over time, Perry's received numerous awards and accolades, including memberships in the American Academy of Arts and Sciences, the National Academy of Engineering, and the Tyler Prize, the Clark Prize, and the Stockholm Water Prize, three of the most respected awards in environmental science. But it was a local recognition that I think provides the best honor for what Perry's colleagues have to say about him, and that came from Dick Luthi, friend and colleague in the Department of Civil and Environmental Engineering. And what Dick said was, Perry has advanced environmental engineering and science as no other. And that's a very fitting tribute. Perry is still actively working to advance the field and the practice of environmental engineering. We've noticed this, that our heroes very often have a hard time really retiring. Tonight, it is just a pleasure to celebrate Perry as one of Stanford Engineering's heroes and to honor him with a token of our admiration. So Perry, if you will join me up here, I will present this. It's a plaque, and so we have a hero's wall just outside, and a duplicate of this will hang on the wall, and I'll put it here safely for while you tell us about how microbes provide unique solutions to environmental problems. Congratulations.
Fine. Thank you so much. Thank you so much, Percy. Ladies and gentlemen, I can't really tell you how pleased I am to receive this wonderful honor from Stanford School of Engineering. You know, Stanford's such a great university. I really know of no others where the faculty have always been so open and interested and willing to work across disciplines. That has actually been the key to the success of the environmental engineering and science program that I came here to help develop when I came in 1962. So I'd like today to tell you something about how I got here, and then a bit about what I've been doing since I've been here. I, like so many other engineering professors that I've talked to, what they've done and so forth, similarly, I too, when I was a kid, I liked to play with chemistry sets and build radios. My favorite text when I was in grade school was in elementary physics. But I really never thought of going to the university, as most kids in Detroit at that time didn't go. There were too many good jobs in the automobile industry, building cars. It was in high school that my math teacher started encouraging me to go, and indeed, she wrote my application to Wayne University in Detroit. They accepted me, and so I went there. Then I had to make a decision of what am I going to do. And I first thought of physics, but they told me at the time there's no job in physics except in teaching, and to do that you had to get a doctor's degree. Well, you know, at that time, well, I was lucky am I even in a university, let alone doing something like that. So then they suggested engineering, and that sounded good, so I went in that direction. In engineering, he had to take a course in each of the disciplines. And in civil engineering, the course happened to be surveying. Now, surveying, the course is outside. I really like camping and being outside and, you know, blowing and so forth. And I said, if that's what civil engineers do, that's for me. That's what I want to do. A required course in civil engineering was engineering mechanics. And I really liked that because that was applied physics. The book was a wonderful book. It was written by Stephen Timoshenko, the father of engineering mechanics and a professor here at Stanford University. I never thought I'd be standing here today having my name added to a list with his name on it. Another required course was in water supply and sewerage. What intrigued me in taking that course became in water pollution control. It was interesting because if you add an organic waste to a water supply, and bacteria eat the organic material, use oxygen, dissolved oxygen decreases, and it can kill the fish unless enough oxygen diffuses in from the atmosphere to prevent that from happening. So the science here involved biology, chemistry, physics, and I thought, and working in a natural environment, and again, tracked it back to my sort of love of nature, really liking the outside. And so I decided to go into that direction. It was called sanitary engineering then. And now I had to go on to graduate school, and so I found that MIT had a good program, applied there, and they accepted me. And so that's where I went. Now my family and all wondered, why would I be going to MIT to get a garbage collection degree? But that's important. Now that's not important, but it's much broader than that. And indeed, when I got to MIT, I really found how broad it really could be. Well, these are the four of the problems that were sort of on the table when I was there. Pathogens was a problem that had been understood and pretty much solved as far as drinking water in the early part of the 20th century. In fact, at the end of the 20th century, the National Academy of Engineering, they looked at the 20 most significant achievements in engineering then, and this is one of that came up as most important because what we had done in the field was primarily responsible for doubling the life expectancy in the United States. It's not a problem that's gone away. We know the problems in Haiti today. We know the problems in developing countries and throughout the world. But at least we understand what the problem. The other one that was most very important was, as I mentioned, of depletion of fish. We knew some treatment processes to help that, but it needed solving. Industrial waste were just emerging. They were all different. We hadn't really the science and technology to handle that problem. And then the nutrients, where nitrogen and phosphorus were coming into the water. We knew at the time that that was causing this problem, the eutrophication, stimulation of the growth of algae. But we really weren't doing anything about it then. So these were on the chart, but at the same time, Cuyahoga River was burning. This is not the first time it burned. Water's not supposed to burn, but there it was. And then when I came here to Stanford, the San Jose treatment plant, brand new, was just built. And in that plant, they bubble in air for oxygen for the bacteria to degrade the organic matter. And at that time, something had happened at the end of the Second World War. We got bubbles like this on our treatment plants, and indeed, foam like this was popping up. It was not only at our treatment plants, but it was in groundwater, it was in rivers, it was all over the country. And then when I went for my master's degree in Chanute, Kansas, first time we really experienced this. This brought home something else. The river dried up. And so what could the people do? They needed water. So they went down, they built a dam below the wastewater discharge. The wastewater moved up to the drinking water supply, and that became their water supply. This is what it looked like at the treatment plant when that happened with the soap and bubbles and so forth. And if you look at the woman on the right there, that glass of water is not a good head of beer. That is drink water. Now the beer drinking went up in the city at the time. But now we know about droughts today in California and how serious this problem is. That's opening because now the refractory organics, the synthetic detergents that were built in Germany during the Second World War because they didn't have fats to make soap, it was a wonderful industrial achievement because it didn't mix with the hardness in water. But this was a problem. This was our first introduction to something that doesn't really break down. So anyway, at MIT, I had 4 professors. These are 3 of them. Claire Sawyer was an environmental chemist. He was working on the detergent problem. I was kind of interested. He wanted me to suggest go on for a PhD. doctor's degree actually, doctor in science. So I worked for him on the synthetic detergent problem for a little bit. But then he decided to want to write the first edition of the textbook on chemistry. And so he left MIT to take a leave of absence. So then I switched to Ross McKinney, who was working on the biological process, working on the science. And this was stimulating because it was just then we were getting away from a very empirical approach, trial and error, to try and understand better how to design a process, what's the science behind it. And so this was emerging. Rolf Eliasson was the head of the program at the time. Now, as it went on, Claire decided not to come back. He wanted to stay with industry. So, being in the right place at the right time, he said, what can they do? So they hired me to replace them. So there I was teaching at MIT. And after I started teaching at MIT, became disappointed in the sense that we had this limited faculty. You saw the breadth of the problems that we were beginning to face, even just in the water area. And we were so limited. We were very good in the little things we did, but we couldn't even get courses in hydrology or hydraulics in our own department because the barriers were too great then. They didn't take our courses, we didn't take theirs, and there's no place else you can go in the university to get something else. So one day, Rolf Eliasson, he became chairman later on, civil engineering. In 1961, he called me in his office, and he said, asked if I ever heard of Stanford University on West Coast and so forth. He said, well, they have a program in water resources where the fluid mechanics, hydrology working together. They're bringing in engineering economics. They're bringing in political science. They're bringing in policy and so forth. And he said they want to add a water quality component to it, and they've offered me a job, and so I'm going to be leaving. So then he turned to me and says, would you come with me? I said, yes, immediately. I went home, told my wife Martha, we're going to Stanford. She said, okay. In 8 hours, I learned about Stanford University, Water Resources Program, been offered the job and accepted it. You don't do that today. I've never been disappointed. Never been disappointed. It's such a wonderful place. They did have the Water Resources group going, but the thing that was surprising to me was that I got friends in School of Earth Sciences. It was easy to do, chemistry, biology, law school, business school. Any place you could go, talk to people that are interested in working with you, and I don't know of any other university like that. And it was because of that that we were able to build this cross-disciplinary program, environmental engineering and science, and immediately became one of the best in the country. So, and that still is the breed here. I don't know why at this university that happens, but it does, and it's so important. And now we have our buildings together where we're all in together from working on energy and environment and so forth. Well, let me go back then to a little bit of what I've been doing as far as science concerned. Now, I just wanted to indicate something important. Claire Sawyer, who left, he and his students, instead of doing what so many are doing, like when I came here in San Jose, they were pouring oil in the aeration tanks to try to tie up the detergents. And they were, where gets water? And they were, excuse me. So, but what he did was look at the science of it, and that top one, what called alkyl benzene sulfonate, or ABS, it had, they recognized it had these branches in it, and that little carbon I drove a little red circle around was, excuse me, was tied to 4 other carbons, and they realized that this was not biodegradable. So, in the branching, the bacteria did not have the enzymes to do that. So they suggested that they straighten out the molecule, or the problem would go away, which it did. Now, we work with detergent manufacturers to test different ways of doing that. In 1964, the problem just disappeared. Take a little more. Well, on the left here, this is San Jose treatment plant without the bubbles. You can see they're coming in. Ross McKinney, my advisor, they were studying that. Most of them people working on the science in that. They had a concept of food to microorganism ratio to do that and applying that as a science. It requires power to grow that air, and about 3 to 4% of the electricity in the United States is used just for that purpose. Bacteria use the waste, about half of it's converted into new organisms. And so we end up with this, what we call sludge. The sludge is taken from here, it's about a 6-hour detention time, the aeration tank, and then is put in anaerobic treatment systems, digesters, as we call them, seen on the right side. And in there, the waste is broken down and converted into methane. So the difference here is, in this process, the aerobic process requires energy. What on the right produces energy in the form of methane, natural gas. Claire Sawyer had the class in which we ran the anaerobic process, and I became very intrigued with that. It seemed like a waste. We should be getting resources out of our materials rather than treating them. But now the digester, the detention time was long, maybe 30, 40 days instead of 6 hours. And so it was thought, well, you can't really use it for anything except very concentrated waste, and they have to be treated at high temperatures. And the thought was, if we understood this process better, could we treat it in more shorter detention times? And so that became my interest. Now, the textbook that we had at the time was written by, when I came in 2 years before, was by Gordon Fair. He's a chaired professor at Harvard, world known. And he had worked with Karl Lemhoff, a German, also well known. And in the book I got, my book, it said, how do you design one of these digesters? Well, you look at the community, see how big it is, and there's so many cubic feet per capita. That's science. That's what you, how many people you have, and then you multiply it by some number. But the science that they had was dependent upon the temperature, though. Because if you work at a higher temperature, then it goes faster. Well, as shown here, they had a couple of different organisms that live on mesophilic, sort of average temperatures, and then there's some work better at thermophilic. But most people, since we got the methane, they could take and heat the sludge up to, say, 35 degrees Celsius, which is 95 Fahrenheit, as an optimum. And for that, they found by putting this sludge in a bottle that took 23 days to get the most amount of methane. So they said you should double that, safety factor to 46 days. So that was the science. Well, in class, we were taught a little bit better than that when you do that in these complex mixtures of bacteria, some of them take it and ferment it and convert the organics into acids. pH becomes acidic, they kill the organisms, unless you have methane bacteria that take those acids and convert them into methane. That was you had to have this balance to make it work right. The other thing that was just coming out, just before, maybe not more than 10 years before, was some knowledge about the organisms that gets methane. First, and this had been hypothesized by the microbiologists for many years, that hydrogen gas, is produced as you remove, if you take organic material, they remove hydrogen from it, put it off as a gas, and then oxidize the carbon. Reduce the carbon to the methane. That was the theory. But a chemist, Buswell, had been convinced himself, and then finally proved just before, not many years before, that the acid, mainly the acid formed acetic acid, which is vinegar. To those who know what acetic acid is, you've got vinegar, acetic acid, And acetic acid is cleaved in the middle where that methyl group we call goes into methane. That's essentially what we knew. Now my first attempt was try to isolate an organism that used acetic acid. Well, it was really naive. I mean, that was really, really, really difficult. So I learned that pretty quickly, fortunately. But I've soon found some friends that had been studying not digesters like we had, but the rumen of cows. Now, this is just like a digester because we don't have enzymes to hydrolyze cellulose, and so we can't eat grass like a cow can. Neither does a cow. No mammals do. But they have this rumen, this stomach, which is full of bacteria, just like we have in our digester. Same thing. And they have in there the bacteria in there eat the grass and so forth, take the cellulose, hydrolyze it, break it down into organic acids, like this acetic acid I told you. And then the cow takes in these acids, and that's what they feed on, that's what they live on. So as far as studying that, you see, if you want to study the cow, you reach into the cow. They fistulated cow, they put a stopper in it so that you have to do this. The young woman's doing. I showed some microbiologists who were working on this. Cornelius van Niel was one of the Dutch microbiologists, came to the United States to Stanford University in 1928. He was at Hopkins Marine Station, and he became one of the most noted microbiologists in the world. He was studying anaerobic processes, especially photosynthesis, anaerobic photosynthesis. He had apparently a wonderful course. He retired in 1962 when I came, and unfortunately never met him. But I did get to know his first PhD student, Bob Hungate, who was at UC Davis, studying the rumen bacteria. And he was working on it, very difficult to do, started studying them one at a time, and they had to blow their own glassware and so forth. Just very difficult. And one of his students was Marvin Bryant, who I got to know very well. I knew them both, but Marvin Bryant very well. Marvin was just fantastic in the microorganism. The work he did on working with symbiotic organisms, very difficult to isolate, but he eventually did. Well, the big question came at this time was why in the rumen does it stop at the acid stage? And in our system, we go all the way to methane. And they were trying to look at the organism and that. And so we sort of worked together. And my students at MIT, when we were working, in engineering, we do mass balances and rates, kinetics, and so forth. And we pieced together using radiotracers and this substance that acetic acid represents 72% of the methane. We also found that we could compute how much of it goes to acetic acid by just looking at normal biochemical pathways. So here we have now acetic acid as being the major acid. We get the rest of it coming from hydrogen that's released from other compounds. So at least that was one step, how important acetic acid is. Marvin Bryant then asked me to a Society of Industrial Microbiology conference, I think it was 1965, to present some of the work. Well, an engineer going to a biological conference. So anyway, I did that, and I presented where we were. We just after I came to Stanford, we had put together I put this in. The paper won the Best Prize award. I said, what is this? Because what was different here is that we ran these digesters at different detention times at that time. And you can see as you get shorter and shorter, the methane production finally gets to a point where about 10 days it starts dropping off. Now, if you look at the particulate organics, or suspended material that was being hydrolyzed and broken down, as it was decreasing at a shorter time than that, but the volatile fatty acids were building up. Now, these volatile fatty acids are the acetic acid, and 2 and 3 and 4 carbon acids that normally in the cow they use. Well, you could see a couple things. Once, if you operated, I said, what is the detention time in the cow's rumen? It's only about 3 days. I said, no wonder the cow you put it 3 days, you washed out. What happened? Because the acetate using organisms had a doubling time of 4 days at these temperatures. And if you operate at less than 4 days, You know, you have one organism, before it can become two, you've taken it away from the system. So they can't grow in it. They're washed out. And that was the secret difference between a rumen and what we did. Well, what it indicated is that if you want to run a biological treatment system, you have to find the doubling time, the rate of growth of the slowest growing organisms in the system. And then you apply a safety factor. For example, if it's 4 days here, say multiply it by 4, maybe 16 days, and it'll work. And now we have all the different biological treatment processes. This become, and I call that, instead of detention time, it's the solids retention time. It's the time of the suspended material that you keep in there, the bacteria. Not the detention time of the organic, the waste, but how long you keep the bacteria in. And so that was a whole difference. Now, how are we going to make advantage of this for industrial waste? Well, what we tried to do had young, we thought, well, maybe if you put in some media for the bacteria to grow on and stick to it, so as the water comes, the waste comes through it, if you have a soluble wastewater come through it, you keep the bacteria in there, but you can have a short detention time for the liquid. So he tried it in their labs over on the far right side there, put in some rocks and the bacteria, and it worked. Now, and so here with dilute waste, industrial waste, room temperature, maybe you could do about 12 hours for something like maybe 3,000 milligram per liter concentration rather than the 30,000 that we had in the sludges. And I just show this picture here taken from that other one. And you can see that little black stuff sitting on top. We thought they kind of probably attached the organism to the solids, but we see they're settling in there. And so Jim Young took those out and magnified them. This is what it looked like. He called them granules. And if you take one of those granules and open it up, you see all this whole mixture of bacteria. And what's really critical here, because there's so little energy available, we get most of the energy out in the methane. Very little energy for the organism, and we have several of them working, each one taking a little piece of it. They have to work very closely together for them to get this energy out of it. You see there's some long ones there, long chains. Well, actually, it's several organisms. We used to call it the fat rod, and it's the critical one that uses the acetate. It's very difficult to isolate that by itself, but when you put it in a mixture, it works pretty well. Well, okay, given that then, using that principle of keeping the bacteria in, depending upon temperatures, maybe keep them in for 20 days or 30 days or 40 days, let the wastewater go through, and all these reactors are now different ones, different people have evolved in them. I want to show you the one on the upper right-hand corner from McCarty Rum Company. EPA told them that they have to treat their waste, that they were, after making rum and distillation, they had this waste and they were putting it into the ocean, and they told them they had to clean it, so they looked at this and they saw this, so they built what you see is that big reactor there using this principle, but they used a plastic media instead of stones because more efficient. And when they finally built the plant, the methane they produced in 5 years, the value of methane in 5 years paid for itself because they were using that methane to distill the rum. And so here you have protecting the environment and making money at it. Now that's ideal. That's what we want to do. So now for industrial waste, organic industrial waste, these are the technologies that are used. I want to come back to when I first came to Stanford, 1962. Rachel Carson had just come out with her book, Silent Spring, about now another refractory organic problem, chlorinated compounds. And so killing the grebes in Clear Lake here. Just a sad story about what was happening and what to do about it. Well, I had in my first mess, Dan Seidel here was in my first class. I think it was 4 people in the class, something like that. And one of them, Dave Hill, came to me and he said he'd like to go on for a PhD. And so he said, I'd like to study pesticides. And he says, I know you're doing anaerobic treatment, so we should try it anaerobic. Well, at that time, everyone said anaerobic treatment, fine. It will not, and if it's not degradable aerobically, it's not going to go anaerobically. And then these compounds are degraded aerobically. So I humored him along and said, well, maybe he could learn something from this and get started. And so it's very difficult at the time because it didn't have good analytical techniques. So he started studying. These are the chlorinated solvents that were chlorinated pesticides that were commonly used at the time. So he finally got analytical procedures worked out and how to get it. So he said he wanted to study lindane. This is the lower one down here. And so, because we were spraying on our agriculture fields at the time, so he went down, got a bottle of the anaerobic sludge from the treatment plant. He put it in. 10 days later, he comes in and says, they're gone. I said, can't be gone. Put some more in. He went back. 10 days later, they're gone. Get some DDT. Put in the DDT, and it disappeared. And then it showed up first, this compound. So this compound is the same as DDT, except the bottom chlorine is removed and replaced with hydrogen. We call that today reductive dehalogenation. I just want to point that out. And then it disappeared. So he tried all those others, they all disappeared. Well, what should we do? Well, it was interesting. I thought, that's really novel, but, you know, they spray it all over agriculture fields. It's all over. And I know at that time there was so much coming in against chlorinated solvents. I was sure that these would all be removed, taken away, replaced by something biodegradable. And they hardly ever go into anaerobic environment anyway. So I didn't do anything more on it. And indeed, we did do away with those compounds. Well, skip 10 years forward. In California, water was becoming a problem. Reusing sewage became something we were working on, people were working on. Orange County in 1976 built the first one where they used a reverse osmosis to try to remove most of the stuff remaining, put it in the ground, and treat that, and then people would take out the groundwater and drink it. So Santa Clara Valley Water District came along, and anyway, Santa Clara Valley Water District came along and asked if we would like to study. They were planning on seeing what would happen and inject it in the groundwater. So we said, sure, we'd like to do that. And another important thing at Stanford that happened at that time was a cooperative group here, computer science, that artificial intelligence, computer science, biology, chemistry, and the three of the people from there got together, and they came up with a way of building. They built computerized gas chromatography, mass spectrometry, so that it takes samples with complete complex mixtures of substances and water, pass it through. They're separated by the chromatograph. They come out. They're bombarded by electrons broken apart in the mass spectrometer. Look at the fragments, the massive fragments, and then the computer science part of it would be to look at those fragments and to give a probability of what that compound was. And that became as a joint effort between people here. And that machine had just come out in time for us to say, now we didn't know. People were worried about carcinogens and all the other things, and so we had it. And at the same time, we were lucky, Martin Reinhardt, who was just getting his PhD in Switzerland. He worked with a professor named Grobe, and Grobe had developed what we called a capillary column. And so Martin Reinhardt came and agreed to come and work with us on it. He brought with him, introduced United States capillary column chromatography. And before that, we used these columns. And when a compound emerged from a gas chromatograph, it was kind of spread out. And then another one we spread out. So they're all mixed together. But with the column chromatography, you got a compound came out like that, another one came out like that, and you can quantify them and so forth. Martin introduced that to the country, had to come here and build his own capillary columns, and it's standards through the world today. But it came there, so we did the analysis, first analysis of wastewater, Orange County, and we started doing that here and looking at these compounds. Well, we were looking at all the compounds that were after going through very advanced treatment, and what we found coming out were these chlorinated solvents. That was what was left after all this treatment. And where did they come from? Silicon Valley, electronic industry, used them in big things to clean up their chips and so forth. Well, so we started that. So we put them in the ground. So we're putting them in the ground down here. And guess what happened? The literature had just come out. National Research Council said these compounds are non-degradable. We put them in the ground, they disappeared. So the students went and said, well, we better look at it in the laboratory. They did aerobic, and of course nothing happened. Anaerobic, they disappeared. So here we had anaerobic processes, and I just wanted to indicate, just a few years later, the National Research Council wrote a report that there's 300,000 to 400,000 sites in the country. Department of Energy, Department of Defense, all industry, all electronics industry, car manufacturing, everybody was using these compounds for cleaning, removing grease. And when they looked at this big site, almost $1 trillion estimated to try and clean this up from groundwater. And what were the two major contaminants? First was trichloroethylene, second was tetrachloroethylene. Same thing we were finding. And they were disappearing anaerobically. Now, let me just show a little bit of what happens. You put these, you get these solvents, you clean up all your parts or whatever, and they get all full and dirty. They put them in a storage tank and call up somebody to take it away when the tank is full. It's very corrosive, the tanks corrode, and so it leaks out. So, you never have to call anybody to come up and pick up your waste because it's gone. Well, where does it go? It goes down the ground, and that was happening everywhere. So it's heavier than water, so it comes down. It goes through the Vados unsaturated zone, it hits groundwater, keeps on going. It may go down hundreds of feet and scatter around. You don't know what, moving all kinds of directions. And then when you have groundwater coming by, it's very slightly soluble. It'll pick up. Now it's slightly soluble, but those slightly soluble concentrations are maybe 1,000 or more times the drinking water standards. They're known. They're suspected human carcinogens. And then downstream, you pick them up, maybe it's a mile or so, a couple miles downstream, you take out your groundwater is contaminated. We had it all around Stanford, from Stanford's industrial park over here, Fairchild, and so forth and so on, Hewlett-Packard. We had these plumes coming in here, but that was throughout the country. And so it was a big problem. Well, these organisms are one possible way to solve it. And it's not easy. So we did field sites. We did some on Moffett Field. We did a test station down there. We've been at Edwards Air Force Base trying to clean up the X-15 rocket plane plume that was moving out to St. Joseph, Michigan. And we did the work for Orange County in there. So it's not that simple. But I got to jump over this fast somewhat. And I just want to indicate what's going on here. Now we find out, and this is complicated. There was some 30 years of work. Microbiologists and engineers all over the world are working on this problem. So, and I've got to tell you all about that in a couple of minutes. My first students, we went down in the laboratory with this PCE, it's tetrachloroethylene, but we call it perchloroethylene. And what happens, the bacteria, again, using that hydrogen. Now, where did the hydrogen come from? You have to have some organisms breaking down some other organic and producing this hydrogen. Okay, and then the chlorinating bacteria use that hydrogen and do reductive dehalogenation, take off the chlorine and replace it with the hydrogen, and that gets it down from 4 chlorines to 3 chlorines. And then my first students found it going down to the 2 carbon one there by this process. Then I had the next student, I said our gas chromatography wasn't good enough to find out what's next, so by the time we come there, next student found out, well, you go much one further, remove more, you get vinyl chloride. Now that's what makes PVC pipe, but with vinyl chloride was showing up every place because of this process. And it's a known human carcinogen. So now this became a real problem. We're taking something bad to make it worse. Well, that would have been the end of the story. I looked and I said, oh my gosh, where do we go from here? And it was in groundwater, as everybody still is. So Jim Gossett, another of my student, now working at Cornell, he was working on this, and he found a culture that took it all the rest of the way to ethene. Now this opened it up because ethene got rid of the chlorines, it's not toxic. So now if we can get it all the way, we can maybe solve this problem using microorganisms, but we got to get it past the vinyl chloride. I can tell you how many different organisms people worked on trying to solve this problem. Initially thought this was just a fortuitous thing that bacteria were doing. You know, if we get chlorinated solvents in us, our enzymes break them down too. So I thought, well, you know, an organism have these enzymes and maybe they just sort of interact with the organism, not giving any benefit. But we found one of a former professor here Alexander Zinder was in the Wageningen at the time. He was here for a year. We tried to hire him here as assistant professor. He was very good. He came for a year, and went through the process to try to get him hired. It takes a long time now to go through and get the dean's office to approve it, and then go through to get all the references. So we finally got a reference to him. I called him up. He was in Switzerland at the time. I said, Alex, I'm going to give you assistant professorship. Why didn't you call me yesterday? I said, why? He said, well, in the Netherlands, they give me a full professor with tenure in head of the biology department. If you would call me 2 days ago, I wouldn't have went to Stanford. Yeah, sure. Well, anyway, he had a student named Chris Holliger, and Chris Holliger found an organism that went through these 2 first steps and showed the organism gets its energy from doing that. It's growing on it. That's how it gets its energy. The chlorinated solvents. Now, hydrogen is the food. We think of organic matter. Bacteria use hydrogen, just like the methanogens did, as their food. And it's oxidized by something, like we use oxygen. These bacteria use chlorinated solvents as their oxidant. They breathe with chlorinated solvents and get their energy and live that way. So anyway, so this went through, so this opened up the whole field. Now we can really, if organisms grow on it, we can build up concentrations and really do this well. So we're looking for organisms. There are many different ones. And then finally, my colleague in Cornell, and he had a Steve Zinder this time, very good microbiologist, and they were working on trying to isolate this. Of course, these organisms are really difficult to isolate. They finally came out one, and it was that could take it all the way through here. Now, this last step was kind of interesting. This last step, it did, but it did by this, it didn't get any energy from it. And it could only do that step when it was doing some of these other at the same time, so it was not very, very efficient. They called the organism Dihelicocoides. We had a sample from Texas, Victoria, Texas, DuPont. We were working at DuPont, and we had a culture in our laboratory that was taking it all away. And we found out that it too was living on it, not like the one in Cornell. And Frank Loeffler, who was at Georgia Tech, he found it also. And they were the same organism, essentially. Dihelicocoides had the same character. But then there was Dihelicocoides was found many, many places. And they were doing different chlorinated solvents. Some would do chlorinated benzenes. They could do PCBs. They could do dioxin and so forth. But they were all sort of the similar organism. And so now the genomes of those organisms have been identified. We got several organisms been identified. Finally, Alfred's organism, the one in Fred Loeffler's, his. Now the enzymes are known, and we know if you look at these organisms, let me just go ahead one more and show book 2016 just came out. Lawrence Adrian, he got a Dihelicocoides. He used chlorinated benzene from Loeffler. The other got one on that. And so they, with that, they named it Dihelicocoides. They decided it's the same organism. They have different of the chlorinated dehalogenating enzymes in them. And the only thing this organism lives on is hydrogen and chlorinated solvents. Where did it come from? Where did they come? They're all over the world. And yet, that's what they live on. That's their soul. There's a cute organism over there. It has one of the smallest genomes. It's like a pancake. And my microbiology colleagues, I don't know why they did this, but when they finally were get together and wrote an abstract to get this name officially named, they put my name on it. That's my organ. I'm really proud of that. I never isolated. Anyway, I just want to show this. Just a whole list of compounds. This hydrogen, the first element in the universe, hydrogen, is used as a food source by all these different anaerobic organisms, except the first one, which is aerobic. All these different organisms. We work with the halogenated organics. It works. Percolate, rocket fuel, Fairchild, Sacramento, big rocket fuel. Aerojet Lab, lots of big rocket fuel in the ground. You can get rid of it with another group of organisms. Chromium, Aaron Brockovich fame, you can reduce that, not get rid of the chromium, but you can make it into a soluble form so it won't move in groundwater. Craig Triddle and Peter Kitnidis going down to Oak Ridge. Uranium, the soluble 6-valent form that moves. By reducing it, you can bacteria convert it into an insoluble form so it doesn't move. And so you can get the selenium and arsenic. But anaerobic bacteria do many, many different things that we never thought possible. Well, I want to switch over now. After all those years, I had a group in Korea. My former student shown on the left here, Jacob Bay, the black shirt, called me up one day and he said, Korea comes up with this world-class university program, which we can bring in senior people to work with us to help improve our program, and if we write a proposal. So I thought, well, I would really like to go back and wonder if it isn't possible to treat more dilute organic waste. We were successful doing industrial waste, but is it possible to do this with very dilute waste like domestic wastewater? I didn't think it was. All our work in the past suggested it wasn't. But we said, well, let's see how far we can go. So we have put in a proposal that was accepted. And through a group of laboratory studies, and then it worked. We could really, in fact, much more. I tell the truth, I never thought this would happen. We could get it down to as good as an aerobic treatment process. We put in a pilot plant there that worked at a wastewater treatment plant, temperatures down to 10 degrees Celsius, 8 degrees Celsius, detention times down there to 4 to 6 hours, just like an aerobic treatment system. And it worked, and the advantages of the anaerobic versus aerobic is more energy neutral, so we didn't have to put in this energy. And since most of the energy goes off of methane, we get hardly any bacteria produced, so we end up with very little biosolids. And 40 to 50% of the cost of treatment is often handling these waste bacteria. And here we can reduce that. We get twice as much heat as well as energy, electrical energy out. And here we have Bill Mitch in our group and Dave Sedlak at Berkeley. We're studying the effluent from our anaerobic system, compare it with the aerobic system. These contaminants, now we got contaminants emerging concern we're worried about. Pharmaceuticals, personal care products. What are they going to do? Anaerobic trophos, we got 96 median percent removal. Aerobic system only 76%. So we got excited by this, and now brings into Craig Triddle. Craig Triddle on our faculty was looking at, because we're developing new treatment processes here, he's working with wastewater treatment individuals at Stanford, and wanted to build a pilot scale system so we could kind of quickly emerge what we're doing in the laboratory to full scale. And he was going to put in an aerobic system, and when he saw what we did in Korea, he switched to make it in an anaerobic system. The system is now in post. This is a Codiga Resource Recovery Center, Stanford University, and Bill Codiga, an emeritus law professor, and his wife Chloe provided money for us to help build this, and Stanford built it. And one of the things Craig wanted as part of that is this anaerobic system. So there it is, ready to start. It's getting there. So this would be the first pilot plant of anaerobic treatment of domestic wastewater, be treating faculty and student housing waste. And we'll be soon seeding it, and hopefully we'll see what happens. I think it's a treatment system of the future. We'll see. I won't be here to see that. But so I want to now just go on and just finish up and say, I mean, all the things we do are based upon the students that we get. And we've had, one thing about Stanford is the wonderful students that come in. And these are my 40 PhD students that I've had over the years working on the different processes. And I just want to say how much I owe to them. I just want to really thank them, and as well as to so many of my colleagues here at Stanford and throughout the world, which has made all these things possible. Now, I want to say something else. I'm hoping these processes will be really expensive and cheap, but cutting the energy. Maybe if we save only 3 or 4% of electrical energy by putting this process in. I think that's important. What are the biggest problem we have today, of course, is climate change. It's a very difficult problem. And how are we going to handle that? We can already see what's going on. But when you look at this as maybe just a few percent, I'd like to always think of a famous biologist, René Dubos, who at the beginning of the environmental movement in the 1970s was talking about think globally, act locally, and I think that's what we got to do. If we can do our 4%, and you can do your 4%, and you can do your 4%, and you can do your 4%, someday we will all put it together, and we will get there. And I think that's what we all have to do. So I like to remember that it's just part. But of course, the reclamation of water and reclamation, climate change is going to affect our water supply. So certainly that's one of the major impacts it's going to have. And so we're getting droughts. The droughts we're getting are probably going to get worse. And so we've got to come up with better technology. And we hope some of this may be part of that. But, I just want to bring up another one that René Dubos gave. I gave a talk many, many years ago at Caltech. And René Dubos was there, and he had a talk titled this, Trend is Not Destiny. And, I was, can I make a 4-word statement that means so much? He was a genius at that. But the important thing, he was an optimist. And he believed if we knew the people, and you can give many, many times, we can all give many times, where if you know what's happening, you know the trend, you can see the trend, and you know it's bad, it's inevitable. Change it. We can change it. We don't have to wait till we get to the worst. We don't have to wait till the climate change, the temperatures go way up. We can see it coming, and we can change. And essentially, that's what he's saying. Trend is not destiny. That's not a new statement. I have an ancient Chinese proverb that says essentially the same thing, and I want to show that. And whoops. Unless we change our direction, we are likely to end up where we are headed. So I think we all want to remember that, and hope we come along. And finally, I'd just like to show you a picture of my favorite animal. And thank you all for coming, and thank you, Sophie.
It represents, which I think we all actually need a little of right now.
Yes.
Are there, would you be willing to take a few questions?
Sure.
So, are there any, yes?
But I took a course called Garbage from him.
Masters?
No, it was an undergraduate course called Municipal and Rural Sanitation. And it was nicknamed Garbage by the students.
Oh.
But it was very enlightening. I learned a lot in one quarter. And in your talk, you didn't say much about Dr. Eliason, so I wondered if you had an anecdote or something to add to your talk.
Just repeat the question.
Yeah, the question, he was wondering about Rolf Eliason, who's the one who brought me here and started the program. And when he came here, he quickly, actually it's a little bit of a story, but we had required courses in civil engineering. And so he had to teach one in environmental engineering and had to do with water and supply and treatment, not terribly interesting. But he had this broad range of experience. So the Stanford, the School of Engineering, we used to have our course, now there are 180 units to graduate, 180 units. Then it was about 250. And so they were trying to weed down that, so they had every department cut out a course. And so Rolf Elias said, as a required course, he says, I'll be glad to not treat mine as required course anymore. And so they said, okay, so they wanted to find someone to volunteer. So he said, now I'm free to teach what I want to teach. And he started teaching this much broader environmental program. And so it went from maybe 20 students to, I don't know how big yours was, maybe 300 or 400. Over half the Stanford students were taking his course, and that was a very successful course. So he made a big difference in introducing the environment to people throughout the university.
Other questions? Yes.
Yeah, are we seeing municipalities going from aerobic to anaerobic in any big way and saving money? Or I understand it's about the same footprint for the plants. Or what's the progress in that area?
What I showed you was the first ever built in the United States.
So it's infancy.
Yes. You know, it's like the first computer when you got it, what it looked like. I'm hoping what, 20 years from now it'll look like. We'll make that same kind of progress. We'll see. There's a lot of hurdles that have to go on, but we just got to introduce it and get people thinking about it. There's a lot of work going on now, people interested in it. We'll just have to see if we can. It's a long process to make a big change like that. We hope it'll happen.
Yeah, so another question now.
See, you asked where the Helicosorides McCarty comes from. The chlorinated solvents, are those all man-made, or do they exist naturally before? And
Repeat the question.
Yeah, the question was whether these chlorinated solvents, because we have made many from the pesticides, the chlorinated, so forth. But there are natural ones, and so we have to suspect that how these organisms came about was in dealing with the natural. There's even some vinyl chloride, very small concentrations that are produced naturally. But there's quite a few especially in seawater and many different organisms that are involved in their metabolic processes producing some. So unless these organisms can do something, I don't know, but there are some natural ones, and I think we have to say, well, probably, maybe, those are what generated them.
In the very far back there?
So that plastic column with the rocks inside it, it's still chained up to the wall down in the basement.
Anyone want to buy it for? We can auction it off.
Do you think if we feed it a little bit on its 50th anniversary in a year or so, will it wake back up?
Oh, I'm sure it will.
Maybe one last question. There we go. Yes.
Barry, I was wondering, when you compare aerobic approaches to anaerobic approaches, and we think of places, the developing world where there's so little wastewater treatment, whether the operability and the ease of use of aerobic is superior to, or anaerobic is superior to aerobic in terms of it being like an appropriate technology in our developing world where there's so little wastewater treatment.
Well, I see the question is whether these anaerobic will become appropriate technology in the future, because aerobic is now, aerobic is 100-year anniversary, they just said, on the first development of aerobic treatment. So that thing's been around for 100 years, it's about time. I think the advantages are there. And we improve things once you firstly do it. We didn't know this, what we have here is their conceptual. It works. It works. We know you can do it. Now, can we improve it? Can we get around into problems that are there? And that'll take time. And I don't really see at this point any major barriers that says that we can't do it. And that it has a lot of advantages. Probably the biggest one besides energy is the low solids production, which is a big headache at most plants in the world. And if we can get rid of that, I think it has really good potential. We'll see. I won't see, but you'll see. Somebody will see. My children will see. My grandchildren will see.
So we have a reception outside. If you have further questions, we invite you to join, but please join me in thanking Perry and recognizing him.